Alright, this is my video guide for lesson 10.1.4. The main goal or the purpose of the lesson is to take a deeper look into tangent lines of a circle and secant lines of a circle. We've seen the word tangent before when working with trigonometry. This is a little bit different, and we'll see what that means as we work through it here. There's some parts of this lesson that'll go quick and some parts that'll take a little bit longer. The last question that we're going to do takes a little bit longer, but it's a great question because it helps us practice kind of all these relationship things that we've seen inside of a circle so far. So let's get started with the first part and start kind of getting to understand what a tangent line might be and a secant line might be. Alright, so that's the idea here, tangent and secant. So far we have studied the relationship that exists between angles and chords in your circle. We're going to go a little bit further here today. So consider all the ways a circle and a line can intersect. Can you visualize a line and a circle that intersect at exactly one point? What about it intersecting twice? On the paper, we're going to draw a diagram, and for us, you're going to be using hopefully the tools in Kami to draw these nicely like I'm going to try to do here. So the first one is going to be just drawing a line and a circle that do not intersect. And so, not too bad for part A. I'm going to take my circle tool. I think I have one. Oh yeah, it's right here. There's a circle and a line that does not intersect it. Alright, that's all they want for part A. And this is just going to lead us into, like no intersection, one intersection, two intersections, three intersections. And so what we're doing next for part B is to kind of do something similar, draw a line and a circle that intersects at exactly one point. If we're able to do this, this is what we call a tangent line to a circle. So let's do that so we can actually see what that would look like, what a tangent line will look like for us. And so we go make another circle here. And now I want a line that is just touching it at one point. So I'm going to draw a line out to here. And it's not going to be perfect because I can't really do it perfectly on my computer here. Trying my best to do it. Something like that though, where the line is just touching that circle at that one point. And I'll try to make that point in red. It's intersecting that at that one point right there. And that's what we call a tangent line to a circle. A tangent line to a circle is a line that intersects that circle at one point on the outside there. Okay? And that's our first time we've seen that, and that's where we're going to underline that word tangent, and that's what it means. A line that intersects a circle at one point, right on the edge there. Alright, so now C, draw a line and a circle that intersected exactly 2 points. If we can do that, that line is going to be called a secant line. And this one is a little bit easier to make, I think. And so I'm going to go for C, use my circle again to create a circle. And now I just need a line that crosses or touches 2 points, and right there is a secant line because it crosses, there's an intersection point right here and an intersection point right here. And that's the idea of a secant line. One line intersecting a circle at 2 points, tangent, one line intersecting a circle at 1 point. And then part D, it says draw a line and a circle that intersects 3 times. I think I even crossed this out of our lesson because, one, you can't do it. The idea is that you can't draw a straight line that intersects a circle at 3 different points. And 2, I just don't want us to get stuck on that and just be like, well, I can't do it, I can't do it. It's like, well, you can't do it because it's not possible. So that's a great answer for this, is to draw a line. Well, it can't because it's not possible. All right. Now we're going to investigate that idea of a tangent line a little bit further in the next problem. This idea that you can have a line that intersects a circle at 1 point. Okay, that's what it's saying here. It might be a good idea to go to the ebook and click on that tangent. They'll have that word highlighted. You can see that book definition of what it really means. But again, it's just what this is here too, a line that intersects a circle at 1 point. So there it is, a line that intersects a circle exactly 1 point is called a tangent. What is the relationship of a tangent to a circle? So this is kind of where we get to actually use an idea of, or a concept behind tangent and how it plays into circles. So if you have tracing paper, you can do this. Otherwise, I'm just going to kind of write out my answer here of what's happening. But it says to investigate this question, carefully copy this diagram onto your paper, and then fold the tracing paper so that the crease is perpendicular to line L and passes through that point P. So what you would be doing is like really folding this circle perfectly in half so that this part of the line falls exactly on this part of the line. We're creasing our circle on this point P right here. If I could make a line where the crease would actually form, we would have a crease forming right down the middle of this circle. All right. And then this is just kind of the idea now, is that your crease should pass through, if I folded it perfectly in half and folded it right through point P, your crease should pass through that center point C. And that says, what does this tell you about the tangent line? Well, the tangent line perpendicular to that crease line. And so what do we know about that tangent line? Well, to the diameter of the circle, which that is right there, to that specific diameter of the circle, that tangent line is perpendicular to it. And really that could be a perpendicular bisector of that tangent line. Another thing you could see about that tangent line is from the center of the circle, out to that point P where the tangent line intersects, that would be perpendicular still, and that would be like a perpendicular radius of the circle, because from that center out to that point that's on the edge of the circle, that would be a radius. And so we get this kind of cool relationship here where you get that 90-degree angle forming, you get a radius, and really that perpendicular bisector that happens from when you fold is really the diameter of the circle, or it's cutting that circle perfectly in half. All right. This is one where there's not much we can do without tracing paper, so it's just nice to watch the video and kind of see what that looks like if it were to be folded and that relationship that happens. We're going to take this one step further in the next problem, and I think I'll be able to do this problem on this video. And then the last problem, this problem right here, I really like it, and I'll put it in the second video. It's a great problem. We're not there yet, but I'm just excited about it. It's a great problem because it's going to practice all the different relationships we've seen, like intersecting chords. We actually have a tangent line right there. We have perpendicular lines with a we have so much in there. I'm excited. So before we get there though, we got to look at this one. All right. Ventura begins to think about perpendicularity in a circle, and he wonders if a radius is perpendicular to a line at a point on the circle, how do we know if that line is a secant line or a tangent line? Because he saw this problem and said, like, well, we do see some perpendicular here with this tangent line because it goes out from that center out to there, and that fold makes it perfectly 90 degrees. But how do we know that that's going to happen with a tangent line and not a secant line? So one of his teammates that's going to help him dissect this question says, well, let's make the assumption here that the line perpendicular to the radius is a secant. So they're going to make the idea that this relationship is going to exist where you could draw a line from the center out to the radius, and it'll always be perpendicular, and they're going to make the assumption that that is going to happen with a secant line. So on the paper, we're going to draw a diagram. We already have that. And what I'm going to add in here is I'm going to add lines. I'm going to put a point here that I'm going to call B, and I'm going to put a point here that I'm going to call A to help me visualize this. So that's part A, or point A. This is point B. And then I believe what they want us to do is to draw these radiuses that would be perpendicular. And so I'm going to take from the center, and I'm going to draw one perpendicular radius. And I know what you're going to already be thinking, like, this doesn't look very perpendicular, but there might be something behind that. One perpendicular radius and a second perpendicular radius to points AC and BC. Okay? And so that was all of part A, is just to make this triangle here. And then Ventura says, after we've made this part for part A, so part A is now officially done with, we move to part B. It says, Ventura adds, I think that CAB, the triangle here, is isosceles. And then, do you agree with it? And for me, I'm going to say, yes, I do agree. And maybe you can think of a reason why you believe this is isosceles as well. But I say this is isosceles because CA is the same distance as CB, because they're both radiuses of the same circle. And so that's what I'm going to say. Yes, CA is equal to CB because they're both radiuses of the same circle. Oops, sorry. Both because they are both radiuses of the same circle. Okay. For C then, we move on. Sandra chimes in with, then angle CBA must be a right angle too. All right, and remember our assumption here. Our assumption is that if you have a radius out to a point on a circle, that must be 90 degrees. And so they're saying CBA must be 90, and then Sandra's jumping in then too, or sorry, they're saying CAB must be 90 from our assumption. And then Sandra jumps in and says, well, then CBA must also be 90 if that's isosceles, because the way an isosceles triangle goes is that angle B has to be, or sorry, angle B has to be the same as angle A because they create the same length. And so when you look at what Sandra's saying, she's chiming in, that must be a right angle too, but Ventura says that's impossible. Saying that we have two right angles in a triangle, he's saying that's impossible to do. And then the question is, what do you think? Do you think it's possible to have two right angles in a triangle? And my answer to that for C is no. It's impossible. Because, and this part I'm not going to write because it's long, and I think you might know this too, so I don't need to write it out, is you can't have two right angles in a triangle because there's only 180 degrees in a triangle. And if you have two right angles in a triangle, that's two 90-degree angles, and two 90-degree angles gives you 180. You have no degrees left to form that third angle, and if you can't form that third angle, then it must not be a triangle. And so what this is helping us do is finally get to part D here. And part D says, explain to Ventura what this contradiction reveals about the line that is perpendicular to the radius of a circle. And so really this is another kind of proof by contradiction here. And we made the assumption that the line perpendicular to the radius is a secant. Well, with what we saw here, that can't be true. All right, that cannot be a secant line because we reached that contradiction where it couldn't form a triangle. And so what this really means is that relationship that we're talking about, if you have a radius that is perpendicular, that would have to be a tangent line and not a secant line. So for part D, you have to just think that the tangent line has a radius that's perpendicular, not secant. Has a radius that's perpendicular, and I'm going to write perpendicular as this little thing here. Tangent line has a radius that's perpendicular, but it fails, it contradicts when you try to do secant, so not a secant. All right. Just a interesting little thing there. I like these kind of questions because what we do is we start with this idea where we got really an idea from the question before saying, hey, we saw that radius is perpendicular to a point on a circle, and then we made an assumption. We showed that assumption was wrong, which in turn proved that, well, we can't do it with a secant, but we know that relationship does exist, so it must only exist with a tangent line. I'm going to do this last problem in video 2, and I'm very excited to do it. It's my favorite problem that we might have done in this chapter.